Okay, so now this one has some intricacies to it, but it's not as tough as it looks. One of the first things we need to know is we need to know what's the distance from here to here. And to get that, we're going to have to find this distance, which is the same on each side. You can see this is symmetrical. Both 90 here across there and both 70 degrees. So what we're going to do is we're going to look at this triangle right here. We know this is a right angle because this is a horizontal dimension here and a vertical dimension here. Remember, that's one of our tricks for finding right triangles is look for horizontal and vertical dimensions. The only dimension that we know of this, we know that this angle here is 20 degrees. We know that. How do we know it? Well, because this is a right angle here, this vertical to horizontal, and we know this angle was 70 degrees, so 90 minus 70 gave us 20 for there. And we can find this distance here. What's that distance going to be? Yeah, there you go. 140 minus 60 leaves us with 80 millimeters. So I'm going to redraw that triangle over here in blue. What we're really interested in out of that picture is just this dimension up here. So according to the 20 degrees that we have for an angle, this missing side up here, I'm going to call that little a, is which side? It is the opposite side. I have the 80 millimeters according to the 20 degree angle. What side is the 80? Adjacent. What trig function is opposite adjacent? Tangent is opposite over adjacent. There's also a cotangent, but we don't care about that one because that one's not on our calculator. So we're going to fill in what we know here. Tangent, 20 degrees equals opposite side, which is A, over the adjacent side, which is 80. We are looking for a side, which means I'm going to make it a proportion, and I'm going to cross multiply. Tangent of 20 times 80 divided by 1. So tangent of 20 degrees, make sure I close my parentheses, times 80 divided by 1, 29.118. So that dimension is 29.118. What that means for us is this dimension down here that we were looking for is 90 minus 29.118, or 60.882 millimeters. This one over here going to be the same. So this blue distance here is 420 minus the 60.882 twice. 420 minus 2 times 60.882 leaves us with 298.236. Any questions so far? So now we need to find the distance from that blue line, the other side of this circle, which will be the same on each side. So we can subtract that out to figure out what that distance X between those round pieces is. We're going to find that in two separate sections. The first one is going to be found using this triangle that goes from this line from the center of the circle to the center of that V. Even though it's sitting on its side, it is still a V. If I drop this down, what do I know about that? It's a right angle. It's a radius of a circle to a tangent. That's a right angle. What do I know about this angle here? Half of the 70, so 35 degrees. The only dimension I know there is my radius. So I'm going to look at that triangle there for a minute. I have 35 degrees. I have 30 millimeters. The dimension I really want is this one here. I'm going to call that B. If I have the angle 35 degrees, 30 is which side? Opposite. B is adjacent. Opposite and adjacent is once again a tangent. Plug in what I know. The angle is 35 degrees. Opposite side is 30 millimeters. Adjacent side is B. That's what I'm looking for. Put that over 1 so I can cross multiply and divide. 1 times 30 divided by the tangent of 35. 42.844. So that dimension from here to here is 42.844 millimeters. What about from here to there? Yeah, that's just a radius. That's going to be 30. So 42 plus 30 is 72.844. That's the 42.844 plus that radius of 30. Now we have to multiply that by 2 because there's one over here. It's identical to it. Which gives us 145.688. That has to be subtracted from the 298.236. To give us 152.548. So that's the distance, 152.548. I'm going to report it as 152.55 millimeters. Usually millimeters, we only go to the 100th of a millimeter. Notice though that during my calculations, all of my previous calculations are rounded to the 1,000th. When I calculate, I always want to keep at least one digit past where I want to round my final answer to. Does that make sense? Because if I'm rounding to that hundredths place all along, my round off errors build up. If I'm rounding one digit past that, I'm rounding down to the thousandths place, there's a good chance I can keep those round off errors from building up and affecting my final answer. Any questions on how we got that 152.55 millimeters? Now, I realize you might be looking at that thinking, that's not that difficult, but I don't know if I could figure that out on my own. It's something that takes time to get used to, looking at these problems and figuring out what do I need to know. Anytime you have a V problem like this, you can always find the distance from the point of the V to the center of the circle. Whether it's along the slope like this or whether it's straight across, you can always find those distances as long as you know the radius of the circle and the angle of the V. That's a very common recurring theme. In fact, everything we do is kind of a recurring theme. It's just it takes time to see it enough that you can see those things popping up in each problem. Anybody feel like they have absolutely no chance of doing a problem like this ever? Not at the moment, but ever. Okay, good. I say at the moment, I realize that one's a little bit new to you. Anybody have any questions off of what we did in the homework? I mean, remember, we're only supposed to do the V block problem, so I don't want to look at any others quite yet. We'll do some of those examples today. But let's take a look at some other examples, and we'll be working on the same homework assignment today, so it'll give you some time to go back over them. One of the applications that we see a lot used to see it constantly, but now it's a little bit less prevalent with some of the more precision tilt tables and stuff like that. But it was a sine bar. And all a sine bar is a very precisely machined bar that has round ends on it and a very, obviously way more precise than I'm capable of drawing, precise platform on it. And the center of these round ends here, center to center, is either exactly 5 inches or exactly 10 inches. In industry, usually they're 10 inches to make them a little bit longer, but they do have 5-inch ones. And because they're very, very precise, I mean, we're talking to within a 10,000th of an inch of that dimension from center to center, we can use them to create very precise angles. So if this is sitting on a surface here, now that again is now not just any table or whatever, it's either a precision surface like a stone, or it's a table for one of the machines or whatever. And what we can do is we can build up a height here. Notice those round parts are fatter than the flat surface. And that is so we can tilt it and still set it on the round part. We can build up a required dimension here that'll create this desired angle here. Now, you'll note what we're really doing here is we're taking this triangle that goes center to center. So it goes like this. And we're just sliding it down a little bit. So we're moving it down to here. But it is the exact same triangle. Again, that's why it has to be so precision machines. Those round parts have to be exactly the same as well. So that what we're moving when we're sliding down, we're sliding this radius and this radius are exactly the same. So that green triangle, I'm going to erase the blue one to get it out of our way. That green triangle contains this angle, which is the angle of tilt of that sine bar. So there are 2 ways we can work with this. Let's say we build up gauge blocks here to give us a dimension. Let's go 2.136 inches. And I want to find precisely what this angle is. Well, from this angle here, this is the opposite side. This is the hypotenuse. What trig function involves opposite hypotenuse? Sine. That's why it's called the sine bar, because it's always the sine that you're given the hypotenuse from the sine bar, and you're going to be building the opposite using those gauge blocks. So now we know the opposite side is 2.136 and the adjacent side is 5. Are we looking for a side or are we looking for an angle here? We're looking for an angle. And when we're looking for an angle, we use an inverse trig function. Sine -1 cancels out the sine. We got to do inverse trig over there. So our angle theta is equal to the inverse sine of 2.136 divided by 5. So second sine, 2.136 divided by 5. 25.2899 or 25.290. Is our angle. Now, we're not going to express that in decimal degrees. We're going to go ahead and convert that to DMS, degrees minutes seconds. So it's 25 degrees. I'm going to subtract 25 off of this. I'm going to take the decimal degrees. What am I going to do to it to convert it into minutes? Times 60. Very good. So I got 17.399. That's 17 minutes. Now what do? I subtract the whole number of 17 and then To make it seconds, I multiply by 60 again. 23.98, so that's going to be 24 seconds. So that's 25 degrees, 17 minutes, 24 seconds is what that angle comes out to be. Now, generally, we're not just doing a build-up and trying to figure out what angle we have. Bless you. Generally, what we're trying to do is we're trying to find or trying to create a specific angle. So let's say the angle we need here is 18 degrees, 40 minutes. We need to know what height we need here. We're going to call that H. And let's say this is a 10-inch sine bar. So obviously we're using the sine, because it's a sine bar. Do we know the angle? Yes, 18 degrees, 40 minutes. Do we know the opposite side? No, that's what we're trying to find. Do we know the hypotenuse? Yeah, that's our 10 from the sine bar. So we make this into a proportion so we can cross multiply and divide. So we have to do the sine of 18 degrees, 40 minutes. So I'll do sine 18, and I have to go to my angle menu here, select degrees, 40, I have to go to my angle menu and select minutes. So sine of 1840 times 10 divided by 1 is 3.2001. In fact, let's go to the nearest 10,000. 3.2006 inches is what that's going to have to be built out. Remember, our gauge blocks go down to the 10,000th of an inch, so we can go down to the 10,000th. Any questions? Okay, so now we talked about tapers a few weeks ago, and a taper is where you have a round piece where the diameter of that piece decreases over time. We might have little d here, big D here, and our length. Remember, taper is inches per foot, so the taper is defined to be the difference in diameters over the length divided by 12. Assuming that length is in inches, the divided by 12 is converted into feet. But what we're concerned about today is something called the taper angle, or sometimes called the angle of tapers. And what that is let's assume we have this diameter here, which is the same as this one. So this would be a complete round cylinder, piece of stuff, round stock. In order to create that taper, what angle would have to be created here? Well, let's take a peek at this. Let's say that my big diameter is 2.350 inches, and my little diameter is 1.115 inches, and my length is 9.500 inches. Looking at this triangle created here, and that is a triangle. This is the angle I'm looking for. Do I know any of those dimensions? Well, yeah, I know this one here. Oops, I don't know where my number went there. I know this one here is 9.500 inches. Do I know this one here? No, but I can find it, can I? because it's half the difference between the big diameter, oops, that should have been this one here, between the big diameter and the little diameter. So if I subtract 2.350 minus 1.115, I get 1.235 inches. I have to divide that by 2. Divide that by 2 gives me 0.6175 inches. So now, according to this angle, which side is the 9.5? Adjacent. Which side is the 0.6175? Opposite. Adjacent and opposite are what trig function? Tangent is opposite over adjacent. So I fill in. Do I know the angle? No, that's what we're looking for. Do I know the opposite? 0.6175. And do I know the adjacent? Yes, the 9.50. Am I looking for a side or am I looking for an angle? I'm looking for an angle. Since I'm looking for an angle, I have to do inverse trig function. The function I'm using is tangent, so I use an inverse tangent. Cancels out the tangent. Theta equals the inverse tangent of 0.6175 divided by 9.500. I get 3.719 degrees. I'd probably round that to 3.72 degrees. Angles are typically rounded unless otherwise stated to 2 decimal places. Any questions? Let's look at another application. Pretend that looks like a circle. And what we're doing is a bolt pattern, a circular bolt pattern, and we're doing bolts that are evenly spaced. How many bolt holes are we putting around this circle in this case? 7. So the first thing we got to find, what we want to find is the distance from one hole to the next. All we know is that the radius of this big circle is going to be, let's say it's 8.5 inches. So what we're going to do with that, we're going to take the center of that bigger circle and connect it to 2 adjacent bolt holes. Can I find this angle here? Sure I can. How can I do it? 360 divided by 7, which is going to give us 51.42857.143 degrees. Correct? Sure. Okay. Well, do I have any right triangles there? Not right now, I don't. But I can make one. First of all, this is an isosceles triangle if I look at those being 2 radii, right? In an isosceles triangle, what happens if I cut this down through here, cut this in half? Yeah, if I cut that in half, That makes that a right angle, and it cuts this angle in half, doesn't it? So half of the 51 is 25.71428, blah, 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 blah. Something like that, right? So we're going to call that 25.71 degrees. So it's 25.71 degrees. And we know, if I look at that triangle, I'm only going to take half of it. So this is the 25.71 degrees. What else do I know about it? .5 on the hypotenuse, yes. Because that is the radius. Which side do I want? Do I want this side? Say no. No, I want this side. That's going to give us this piece here, which is half of what we want. We'll have to double it once we find it. You get the distance between center to center between both holes. So, given this angle, the side I'm looking for here is what side? Opposite. The side I have is the hypotenuse, which is what trig function? Sine theta is opposite of hypotenuse. So, we're going to plug in what we know there. Do I know the angle? Yeah, 25.71. Do I know the opposite side? No, that's what we're looking for. Do I know the hypotenuse? I better, because I can only have one unknown. Am I looking for a side or am I looking for an angle? A side. If I'm looking for a side, I put my trig function over 1 so I can cross, multiply, and divide. So that's going to be sine of 25.71 times 8.5 divided by 1. Come on, pen. So we get 3.687. So that's that distance, 3.687. What do we have to do to that to get our answer? Times 2. 7.375. So that's center to center distance, 7.375 inches. What do you think? Not so bad? Your calculator's got that reverse logic. So on page 358 through 361, should be able to do all of those problems. If you just want to do the odds, that's fine. Pick out if some of the evens look difficult, maybe give those a shot. But I'll let you guys have the last 15 minutes to get started on those.